Scientists achieve 43-second fusion breakthrough. Infinite energy closer than ever? Imagine holding a tiny piece of a sun's fiery core in a controlled environment for nearly a full minute. That's precisely what scientists achieved in a groundbreaking test that brought humanity 43 crucial seconds closer to harnessing limitless clean energy. But here's the reality check. Infinite energy isn't landing on our doorsteps tomorrow. What happened in a German lab, though, marks the most significant milestone in fusion science history, and we're not exaggerating. Deep inside the Wendelstein 7X reactor at the Max Planck Institute, a team of scientists pulled off what seemed impossible, maintaining a stable plasma at reactor-grade performance levels for a full 43 seconds. For context, plasma, the superheated gas that drives fusion, needs to be contained at temperatures hotter than the core of the sun. Think 54 million degrees Fahrenheit. That's not just hot, it's a technical miracle. For those unfamiliar with fusion science, don't worry, we've got your back. Let's break this down. Fusion plants work by heating hydrogen atoms so intensely they fuse into helium, releasing vast amounts of energy. The challenge? Keeping that reaction stable and self-sustaining. Up until now, maintaining high-performance plasma has been like trying to hold water in a leaky bucket. Within seconds, it either cools down or destabilizes entirely. This historic test overflowed with clever engineering. The scientists didn't use the more common tokamak design. Think donut-shaped reactors. Instead, they relied on the world's largest stellarator, a complex 3D shape that requires less energy to maintain containment over time. Fusion's ultimate hurdle isn't just heat. It's sustaining that heat long enough to generate net energy. And stellarators seem to offer a promising alternative path. So how did they do it? Science meets teamwork. Here's the play-by-play. 1. Microwave beams. Targeted bursts of energy akin to a high-tech microwave heated the plasma. 2. Hydrogen pellets. 90 precisely timed injections of frozen fuel kept the reaction fueled. 3. Global collaboration. The US Oak Ridge, Spain, Kiamat, and Hungary, Hunren, all contributed critical components. Here's the controversy. Fusion skeptics argue stellarators are too complex to scale, while believers see them as the long-term solution. Should the world focus on simpler to build tokamaks or bet on these intricate stellarators? It's a debate that could define energy policy for decades. For 43 magical seconds, the team hit a triple crown of fusion, a balance of heat, density, and containment time. While no electricity was generated, this proves stellarators aren't just theoretical, they're functional. This wasn't just a quick burst, said Prof. Thomas Klinger, lead researcher. It shows we can maintain conditions essential for real power plants. But don't get tangled in almost there seminar speak. Every second counts. Previous records for containing high-performance plasma were measured in fractions of a second. This 43-second marathon is the fusion equivalent of running a 100-meter dash when your competitors only manage sprints. It proves that science isn't theory, it's tangible progress. So what's next? Sustaining the reaction longer, scaling the design, and turning this scientific curiosity into a power plant-sized solution that could supply millions. For now, it's a profound reminder that fusion isn't a fantasy. It's a possible reality, 43 seconds closer than we were yesterday. We want to hear from you. Stellarator versus tokamak. Where do you put your money? Should governments prioritize these complex but efficient designs or stick with the tried and testing tokamak approach? Let's debate in the comments below. As featured in our related stories, insert anchor links as an original article, preserving URLs. SBX Cars, your premium destination for rare supercar auctions, powered by Supercar Blondie. Nuclear fusion breakthrough. German scientists reach 20 million of a Celsius milestone. Imagine a world where energy is so abundant and clean that it could change everything about how we live. That's the promise of nuclear fusion, and it's closer to reality than you might think. But here's where it gets controversial. In a world where the quest for sustainable energy is more urgent than ever, one European nation has taken a giant leap forward. Germany, with its rich cultural tapestry of castles, automobiles, and delectable treats like beer, sausages, and gummy bears, has once again surprised the globe with a scientific breakthrough that could redefine our future. The pursuit of carbon neutrality by 2050 is a daunting task, yet it's a goal that humanity must achieve to preserve our planet. As we move away from fossil fuels, renewable energy sources offer a beacon of hope. However, these sources, while promising, have their limitations. Until now, German scientists have achieved a milestone that seemed impossible just a few years ago. They've reached a temperature of 20 million degrees Celsius, a feat that pushes the boundaries of what we thought was possible according to the laws of physics. This breakthrough could be the key to unlocking a new era of clean, sustainable energy. The process they've harnessed is nuclear fusion, the same energy source that powers our sun. By replicating the fusion of light atomic nuclei into heavier ones, scientists believe we can generate eco-friendly, continuous power with minimal emissions and radioactive waste. Unlike traditional nuclear fission, which splits atoms apart, nuclear fusion brings them together, offering a safer, cleaner alternative. The quest for nuclear fusion is not new, but recent advances are making it more attainable. The Max Planck Institute for Plasma Physics has been at the forefront of this effort, focusing on a stellarator called Wendelstein 7X. This massive device, with its 50-foot diameter and 16-foot height, uses low-density electrically charged hydrogen gas as fuel. In Greifswald, scientists achieved a world record-breaking fusion reaction that lasted for 43 seconds. This feat was made possible by the stellarator's unique design, which creates twisty magnetic fields to contain the hot, charged plasma fuel. For nuclear fusion to occur, 3 conditions must be met: ample temperature, sufficient density, and adequate entrapment time. These 3 factors are known as the triple product, a crucial metric in fusion physics. The Wendelstein 7X achieved a triple product record, with plasma reaching temperatures over 20 million degrees Celsius and peaking at 30 million degrees. This high-performance plasma was sustained for 43 seconds, a significant milestone in the journey towards power plant-capable stellarators. As we stand on the brink of a new era in clean, sustainable energy, the implications of this breakthrough are profound. Power plant-capable stellarators might be a reality sooner than we think, offering a solution to our planet's energy needs. The question remains, are we ready to embrace this change and enter a new era of clean energy? Controversial point and thought-provoking question. This achievement is a game changer. But some experts argue that nuclear fusion might not be the silver bullet we're looking for. What do you think? Is nuclear fusion the future of energy, or are there better alternatives we haven't discovered yet? America's artificial sun, the future of clean energy and its controversies. The dawn of America's artificial sun is igniting deep divisions among tech elites, climate activists, and energy giants. It sounds like science fiction, but the United States is closer than ever to creating a man-made star that promises limitless, carbon-free power. This ambitious effort already has experts celebrating breakthroughs and skeptics warning of wasted resources. And the debate is only heating up. In a nutshell, the United States was racing to build an artificial sun that could deliver endless, zero-emission energy. Engineers at MIT have engineered new metal alloys capable of surviving a fusion reactor's blistering heat and radiation. International collaborations from ITER in France to private sector partnerships are accelerating progress. If fusion becomes practical, it could transform global energy security and strengthen climate resilience. Why fusion energy could change everything. Nuclear fusion is the process powering the real sun. Lighter elements fuse into heavier ones and unleash enormous energy. Unlike conventional nuclear fission, fusion produces virtually no greenhouse gases and relies on deuterium, a form of hydrogen that can be extracted from seawater. The dream is clear: green energy without the carbon footprint. But here's where it gets controversial. Replicating the sun's core on Earth means confining plasma, superheated ionized gas, at temperatures exceeding 300 million degrees Fahrenheit. Most experimental reactors use donut-shaped chambers called tokamaks to keep this plasma in check with powerful magnetic fields. The ultimate goal is net energy gain, meaning the reactor produces more power than it consumes. A milestone scientists have chased for decades. For years, the biggest roadblock has been materials. Reactor walls endure punishing radiation and atomic bombardment that cause metals to swell, crack, or become brittle. Tackling these fusion-induced metal failures is essential to moving from lab experiments to commercial planes. MIT's material breakthroughs. A team led by Professor Julie at MIT's Energy Initiative have made headlines by discovering that mixing ceramic nanoparticles into iron-based alloys dramatically reduces damage from helium atom created during fusion reactions. These helium atoms typically burrow into the metal's crystal lattice, form microscopic bubbles, and eventually cause the walls to fail. The MIT solution dispersed tiny grains of iron silicate throughout the metal so these harder particles replace or trap helium atoms before they can coalesce. In tests, an alloy containing even a few % of iron silicate cut helium bubble formation by about 50%, potentially doubling or tripling the lifespan of reactor components. And this is the part most people miss. Similar approaches in Japan's advanced tokamaks, operating at around 180 million degrees Fahrenheit, have yielded comparable gains. That parallel success suggests the MIT discovery is no fluke, and it could fast-track fusion commercialization. Building the fusion future. The race to a working fusion power plant isn't happening in a vacuum. The United States has joined forces with international projects like ITER in France and dozens of startups at home that are exploring next-generation reactor designs. Professor Lee's team is even experimenting with 3D printing to manufacture complex parts faster and cheaper. The current roadmap aims for a prototype fusion reactor demonstration by 2030. If successful, this could mark the first time we capture more energy from fusion than we put in, opening the door to pilot power stations in the following decade. What lies ahead for fusion energy? As America pushes forward with its artificial sun, technical hurdles remain. Beyond materials, engineers must solve challenges related to plasma stability, efficient heat extraction, and overall cost reduction. Each advance brings us closer to a future where power plants mimic the sun, delivering clean energy on demand. Some critics argue that investing billions in fusion diverts attention from mature renewables like wind and solar, which can be deployed now. Others counter that fusion's potential scale and reliability are essential to meeting global energy needs as populations grow. Where do you stand? Should fusion be our top priority, or is this star-creating quest a risky distraction? Share your thoughts, then join the debate below.